Okay, I've started the live stream now, so we can get started in a minute. I see a lot of people are in the room. That's great. Let's see over here. Okay. Okay, I assume people are still hearing me, right?
Yes, we can hear you in the room.
Okay, excellent. I think we can get started. It's 15 past, according to what I see on my phone over here. Okay, let's get started. And it looks like the live stream is okay too. If there's any issue, let me know. So welcome to lecture 18, everyone, for digital design and computer architecture. Unfortunately, I'm a bit under the weather, so I decided to do this remotely. Hopefully my voice will survive until tomorrow, but let's see. We're going to continue our journey on branch prediction in this lecture. I think this is really a fascinating journey, and we're going to cover lots of ideas all the way from 1960s to very recently 2020s. So hopefully it'll be fascinating. Remember, we started branch prediction last week, but we didn't really cover a lot of algorithms except for very simple ones. Today, we're going to cover a lot of interesting algorithms that have greatly impacted the performance of high performance microarchitectures. And a lot of these ideas actually made their way into lower performance systems as well. So this is basically what we're going to be done with today, branch prediction. Tomorrow, we're going to start talking about some alternative architectures like VLIW, systolic arrays. Systolic arrays are heavily employed in machine learning accelerators, for example. So it will be a different, let's say, set of classes that we will cover tomorrow until we get to the memory hierarchy. Okay, these are the readings, just to remind you. As I said, I'm going to cover a good chunk of this McFarlane paper over here, which I would recommend you to read. And remember, we talked about different ways of handling control dependencies, and we dismissed some of them, like stalling the pipeline. Doing something else doesn't help single thread. So we were guessing the next fetch address, and we're going to talk about guessing the next fetch address. And I expect that we're not going to cover the other ideas. You can find the other ideas in the backup slides. We had a brief overview of these in the last lecture, but we're not going to go into them much. Okay, remember in the last lecture, I motivated the importance of the branch problem with this example. I will not go through this again, but basically if you have a 20-stage pipeline that's 5 wide superscalar, ideally you would get 100% accuracy and you get 5 IPC, right? But if your branch predictor accuracy is 60%, under the assumptions that we have made, you would fetch 800 extra instructions, 800% extra instructions. As opposed to fetching only 100 instructions, you would fetch 900 instructions basically. And that's a lot of extra energy. And also your performance goes down to 5/9 IPC as opposed to 5 IPC. And this is 60%. 60% is better than random luck. And you may be lucky to predict 60% on some hard to predict branches basically. And if you go to 90%, it's better, but it's not that great still. Basically, the processor fetches 200% extra instructions. Basically, 2 out of 3 things that it does is useless. You can think of it that way also. And its IPC is 1.66, which is not 5, far away from 5. And this is 90%. 90% is actually quite good, especially if the branch is hard to predict. Okay, and we were talking about basically how to predict conditional branches, especially. And this is the fetch stage we constructed. So I'm going to construct again quickly. Basically, for a given, if you want to predict the next fetch address while you're fetching the current instruction, you basically need to figure out the target address of the instruction as well as the direction of the instruction. So direction of a conditional branch can be taken or not taken. If the direction is taken, you should really jump to the target address that's calculated somehow. But you don't have time to calculate the target address because you need to do this in a single cycle, because you need to fetch the next instruction in the next cycle while you're fetching after you fetch the current instruction, right? So we introduced a structure called the cache of target addresses or branch target buffer, which is indexed with the program counter of the current instruction, current branch, but you don't know that. And if the instruction previously executed and computed a target address, you would write that target address and associate it with the program counter in this branch target buffer structure. And if you fetch the same instruction again, you would index this branch target buffer and you would get the target address, and you don't need to compute it again because target addresses don't change for conditional branches as we discussed in the last lecture. So that's how you get the target address of the branch instruction without even decoding the branch instruction, basically. And also concurrently, you index a direction predictor that tells you whether the branch should be taken or not taken. That's the guess that we're going to make, basically. If the branch is taken, predicted as taken, and if the cache of target addresses provides a target address, we predict the next fetch address as the target address supplied by the branch target buffer. Otherwise, either the branch predictor, direction predictor says the branch is supposed to be not taken, or we don't have a target address for it yet, then we predict it as not taken, basically. And it's PC plus 4 in MIPS, but PC plus instruction size in the general case. That's the next fetch address prediction, basically. And this is really the complete, simple fetch engine, if you will. This will become more complicated, as we will see in this lecture, but we're going to talk a lot about the direction predictor prediction mechanisms. So what goes into this direction predictor, basically? And this is where we stopped yesterday. We were going to talk about some simple direction prediction schemes, which are listed over here first. And then we're going to build up to more sophisticated direction prediction, which I added toward the end over here. But first, we're going to start with compile time or static direction prediction mechanisms. And then we're going to talk about more dynamic runtime, hardware-based branch prediction mechanisms. So hopefully you're ready for the journey. And initially, compile time prediction mechanisms were very, very powerful. They still have their place today, but we will see that they're not going to be as accurate as runtime or dynamic prediction mechanisms. But for some branches, they could still be quite effective, especially very, very biased branches, for example, they could still be quite effective. So let's talk about some of these static branch prediction mechanisms. Actually, we have seen some of them. Certainly, we have seen the always not taken one, right? Basically, when we construct our original pipeline in lecture 14, we said that, okay, let's predict the next fetch address is PC plus 4 in MIPS. Clearly, you're predicting always not taken in this case, and this is very simple to implement. There's no need for a BTB even, because you never need the target address, because you're never predicting the branch as taken. There's no need for direction prediction, clearly, because it's always not taken, right? Unfortunately, this is low accuracy, as we discussed. You get only 30 to 40% prediction accuracy for conditional branches. And as we also discussed last time, compiler can actually make this more effective. It can lay out the code such that the likely path becomes a not taken path. And this leads to a more effective prediction accuracy, but it's not always possible to do this, as we discussed last time. And it's also, if your input set is not representative at compile time, doing this may actually hurt your performance if the compiler gets the directions wrong based on the profiling set. And we discussed this, so I'm not going to talk about this, but keep it in mind. All of the static branch prediction mechanisms have the input set representativeness problem if you're doing it based on some profiling mechanism. Okay, that's always not taken. Always taken, again, you don't have no direction prediction, but you need to have the BTB in this particular case because you need the target address. You get better accuracy, 60 to 70% on average, which is not bad. The reason is most branches are usually taken. The reason is you have a lot of loops in a program, and loop branches are usually taken. Imagine a loop where you're adding two 1 million element arrays. That loop branch will be taken for 1 million minus 1 times, right? So the accuracy of an always taken prediction is great in that particular case, and clearly the accuracy of always not taken is terrible for that loop branch, right? So these are called backward branches. Backward branch is a branch whose target address is lower than the branch PC itself. Because if you think about the code over here, you have the branch over here, and then you loop back to an earlier part in the code, and that part has a lower address. That's why this is called a backward branch, basically. I mean, technically, it doesn't have to be that way, right? But anyway. So there's also another interesting static prediction mechanism, which is called backward taken, forward not taken, BTFN. This basically tries to distinguish between loop branches and other branches, and it predicts the backward branches as taken and other branches as not taken. Now, it turns out this was shown to perform better than always taken because other branches tend to be not taken sometimes. But this is static again, right? It's just a heuristic that says loop branches should be taken, other branches should not be taken. This is clearly not true, right? Other branches sometimes are taken, depending on a condition. For example, if you have an if a is equal to 5, then you branch. If a is equal to 5, you actually branch. Okay. So these are very, very simple static branch prediction mechanisms. Let's make them more sophisticated. So profile-based branch prediction mechanisms are a little bit more intelligent, let's say. Compiler determines the likely direction of each branch using a profile run, using some representative input sets, hopefully. And it encodes that direction as a hint bit in the branch instruction format. Now we're actually going into per branch prediction mechanisms, right? For each branch, compiler determines a likely direction. And each branch instruction has a single bit saying the hint bit. And this bit indicates whether the branch should be predicted taken or not taken based on the compiler's profiling information based on what it knows about the program and input set, but based on its running of the program, basically. So this is a big advantage compared to prior techniques that we discussed, prior 3 ones, per branch prediction. Now you can distinguish between different branches clearly, more accurate than schemes in the previous slide, hopefully. And it's accurate if the profile is representative, of course, right? Never forget that profile representativeness problem doesn't go away. But the downside is now we're modifying the ISA, instruction set architecture. Right? It requires hint bits in the branch instruction format to indicate whether the compiler's preference for this bit is taken or not taken. But it's not very costly, actually. Almost all ISAs that I know of have these hint bits. And these could be very useful if the compiler does a good job. Unfortunately, the accuracy depends on dynamic branch behavior. For example, if you look at these 2 branches, these are 2 execution timelines that I show over here. Let me explain this a little bit. Basically, I show you 20 instances of one branch. The first instances are all taken. T means not taken. The first 10 instances are taken. The next 10 instances are not taken. Because the compiler can encode only one bit, saying this branch is likely taken or like not taken, it will encode either taken or not taken for this one. And it will, regardless of what it encodes, it will get 50% accuracy. The second one is basically alternating between taken, not taken, taken, not taken, taken, not taken outcomes in consecutive executions of the branch. So if you look at the history of the branch, this is what you would see across the program. And this is 20 iterations, let's say, 20 executions of the branch. Again, you would get 50% accuracy with a single hint bit over here, because the compiler has only one possibility to encode. But one would argue that these are very predictable branches, right? As a human, I can predict what's going on if I actually see this sort of history. There's a nice pattern to this, and we will try to predict these branches very, very accurately because of this nice pattern. So, but the profile-based mechanism cannot do this, as we said. And also, accuracy depends on the representative of the profile input set. So if you look at this branch, again, another branch, you can see that 18 of the instances are taken, and then the remaining 2 instances are not taken. If the compiler's profile input set is representative, it would encode this branch as likely taken, and it would get 90% accuracy on this branch. That's great. But if the compiler's input set is not representative, it would encode this branch as not taken. And at runtime, you would see this history, and this history would lead to only 10% accuracy. Now you can see the downsides of a potentially, or dangers of a potentially non-representative profile input set, right? You could get either 90% accuracy if the profile is good, you could get 10% accuracy. And in real life, unfortunately, input sets are so wildly different from each other in general that you could get 10% accuracy sometimes. So imagine, for example, you have a sorting program and you're sorting integers in a big array. If that array is initially sorted, then your branches are going to be potentially, let's say, always not taken, right? Same branch. If the array is completely random, meaning not sorted, then you're going to do a lot of operations to do comparisons, and the comparisons will not match, and your branches are going to be more random, let's say, or maybe less likely to be in one direction. So basically, based on the input set that you have, you get significant difference in accuracy, and compiler may not be able to accurately detect the input set, determine a representative input set, because input set is very dynamic in real life. Especially today's input sets, right? We put a lot of data into our programs, like machine learning, for example. They may be completely different from each other. Okay, so profile-based, still, it's actually a very interesting idea. Okay, the other idea is to have program-based or program analysis-based prediction. This is also very interesting. And the idea is to use heuristics based on program analysis to determine statically predicted direction. So this is different. It's not using profile. It's using heuristics. And this paper actually is a seminal paper that talks about branch prediction for free. Let's say it's not for free. There's some compile time analysis that you need to do. So what are these heuristics? For example, this paper uses some heuristics. It predicts branch less than or equal to 0 as not taken. Why? Because it reasons that negative integers are used as error values in many programs, and branches that are testing these error values are usually not taken because your program doesn't usually generate errors, which makes sense, of course, but it's not always true. Example, loop heuristic. Predict a branch guarding a loop execution as taken. Basically, there's a branch guarding a loop. You have an if, and based on that condition of the if, you execute the loop or don't execute the loop. These folks say that in most cases, those loops are executed because programs do things, interesting things in the loop. The real kernels of the programs are in the loops. And most of the time, the guarding branches are guarding against some errors, for example. And usually there are no errors in the program. So execute the loop, basically to predict that as taken. If you're comparing, for example, a pointer and floating point, predict not equal. I don't know why people would do that, but usually floating point comparisons do not match. Usually two comparisons of two floating point numbers do not match, and usually comparisons of two pointers do not match also. So these are two different things. If you're comparing two pointer values and you're comparing two floating point values, and usually they're not equal That's what they're saying. And this makes sense, actually. So you can basically read the paper to see more example heuristics. These don't require any profiling, as you can see, because these are basically semantic based. But heuristics may not be representative or good in this case. And it requires compiler analysis and ISA support. This is true for other static methods as well, as we discussed. Okay, but these folks actually show that at the time and the programs they have examined, you get 20% misprediction rate for branches if you actually employ these heuristics. So it's not bad, 80%. I would argue that in existing systems, it's going to be much harder to get to that level, especially with hard to predict branches. And the difficult part is really the hard to predict branches today. Okay, let's talk about another static branch prediction scheme, which is a programmer-based prediction scheme. Here, it's not the compiler, but the programmer. For example, I'm a programmer, I'm programming the code, and I have some idea about where this branch is likely to go. And I provide that likelihood to my program with some pragmas. Basically, pragmas are used in programming language to qualify a branch as likely taken versus likely not taken. Clearly, if I do that, this doesn't require profiling or program analysis, no compiler support needed. And programmer may know some branches and their program behavior much better than other analysis techniques because there's some semantic information that other analysis techniques cannot capture, which is the programmer's intent. But again, programmer is not omniscient because programmer doesn't know the data input that's going to come into the program. So those data-dependent branches are going to be very hard to predict this way. But some other branches that may have some semantic information that's visible to the programmer can be predictable. Clearly, this requires some now programming language support as well. How does the programmer specify likelihood of takenness or not takenness to the compiler and to the ISA, underlying ISA? And probably this burns as a programmer right now, right? As a programmer, you normally don't think about branches, but maybe sometimes you should if you really want to get high performance. Okay, this brings me to Pragmas. This is essentially how hint information is communicated by the programmer into the hardware. These are keywords in a programming language that enable a programmer to convey hints to lower levels of the transformation hierarchy. Okay, so these are some examples. This basically here, if X, I put a likely over here saying that programmer thinks this is likely going to be taken. So you're likely going to execute the stuff that's in the parentheses over here. If unlikely error, programmer thinks that this branch is unlikely to be taken, basically. And this gets communicated to the underlying compiler. Compiler encodes these likely or unlikely as hint bits in the ISA, just like it would use in its profiling. And many other hints and optimizations can be enabled with Pragmas. I show you one example of Pragma over here. But whether a loop can be parallelized can be also hinted by the programmer so that the compiler can do more analysis. For example, OpenMP, which is the parallel programming paradigm that's used in many high-performance machines, has this Pragma saying Pragma OpenMP parallel. And this is the description from the OpenMP manual. This directive explicitly instructs the compiler to parallelize a chosen segment of code. And this is done by the programmer. Programmer thinks, okay, I think this part of the code can be parallelized automatically by the compiler. So I'm going to put this into my program as a Pragma, and the compiler or anything else downstream, it could be the hardware as well, interestingly, is going to try to parallelize it. So these are actually very powerful words that can be used by the programmer. Of course, if the programmer is wrong, then the branch prediction may go wrong or parallelization may not succeed, right? So programmer can always be wrong. That's always true, basically. Okay, basically, we've covered all of these static branch prediction techniques. I think the ideas are relatively simple over here, and all of them can be combined. You can have profile-based, program-based, and programmer-based techniques. How would you do that? This is interesting, basically. You may have a single hint bit. How would you determine the single hint bit based on all of this information that you get? Profile, program, and programmer-based. They may be contradicting each other, right? This is actually a tough nut to crack, let's say. If the programmer says likely taken, if the profile says likely not taken, and if the heuristics say something, I don't know what it is, then how do you decide whether which hint bit to encode, taken or not taken? I'm not going to go into the details of it clearly, but there's some research that was done on that topic. What is the common disadvantage of all three techniques? Well, I think the common disadvantage is actually in the slide, which is they're static. Basically, they cannot adapt to dynamic changes in branch behavior. As a result, very predictable looking branches like taken, not taken, taken, not taken, taken, not taken, taken, not taken, that behavior is not predictable 100%. It's predictable only 50%, as we discussed, using a hint bit, right? Basically, this is because you cannot adapt to dynamic changes. But clearly, this can be mitigated by a dynamic compiler. Remember, we talked about binary translation and dynamic compilation, just-in-time compilation, or recompilation while the program is running. You can do this, but not at a very fine granularity, meaning whenever the branch changes behavior, every instance, like taken, not taken, taken, not taken, taken, not taken, taken, not taken, recompiling that is very difficult, clearly, because recompilation has its overheads. But some of the branches that change behavior at a coarser granularity, like every 1,000 instances, every million instances, every billion instances, a dynamic compiler can capture that and adapt the hint bit that's used in the ISA. And I think that could be powerful, clearly. And we've seen dynamic compilers. This is basically a compiler that generates code at runtime and keeps recompiling the program, adapting to the information that it obtains based on the profiling of the program while it's running. And one of the pieces of information can be the branch directions, right? And based on the branch directions that are collected by the hardware and supplied to the dynamic compiler, you can actually change the program's hint bits. And this is actually used heavily in real life. Java, just-in-time compiler, Microsoft Common Language Runtime are examples. And we've also seen examples in this course earlier for different reasons, but dynamic compilation can actually make your programs run much faster. And these are example processors that actually employ dynamic compilation. Okay, so that brings me to the end of the compile time techniques. These are relatively easy ideas. We're going to go into more sophisticated ideas. If there are any questions, I'm happy to take them at any time, actually. You can feel free to interrupt me. This is a good time. I cannot see any hands or anything, but maybe TAs can handle that if there are hands. And if there's nothing, then I'll continue. Okay, now we're going to jump to dynamic or runtime prediction techniques. By the way, feel free to interrupt me by speaking up if there's something that comes up, because I cannot see everyone easily on the screen. Okay. Runtime techniques are very heavily employed in existing processors. We will see actually existing processors are sophisticated and they dedicate a lot of hardware to these runtime prediction techniques. Let's talk about what they are. And clearly, the idea is to predict branches based on dynamic information that is collected at runtime, usually by hardware, actually almost always by hardware in existing systems. Clearly, there are some advantages and disadvantages. One is you can predict, the advantages are you can predict based on the history of the execution of the branches. Every single branch, you can have a different history, basically. And we're going to see different levels of history also. So it's going to be fascinating, in my opinion. We're going to use machine learning techniques to actually understand that history or learn that history, learn the correlations in the history of execution of branches much better also. And those machine learning techniques are actually going to be employed in existing systems. They're already employed in multiple processors today. But they're not just based on machine learning. There are other interesting ideas, algorithmic ideas as well. So if you can learn the history better, then you can adapt to dynamic changes in branch behavior much better, as opposed to using static techniques that's based on a single hint bit. And there's no need for static profiling also, because profiling is done dynamically, naturally, while the program is executing on the data set that the program is currently dealing with. You're not dealing with some other data set that you don't know whether is representative of the execution time. You're basically dealing with the current data set that's actually the program is dealing with. So input set representativeness problem goes away with dynamic branch prediction. But of course, this is more complex. We'll see there will be a lot more hardware that we will add. And more complexity leads to higher area cost as well as higher latencies in prediction. Looking at a single bit coming from the instruction format is easy. You don't need to do any computation, but we will see that we will need to do computation. As you do computation to predict the branches, then your critical path at the fetch stage may increase. And you may actually need to have a much longer critical path or break it into multiple cycles. And remember, whenever we break a pipeline stage into multiple cycles, we're worsening the branch prediction penalty. And in fact, here it's even worse because we're lengthening the time we need to detect, to decide on what's the next fetch address. And if it takes 10 cycles, if it takes 10 cycles for us to have the next fetch address, we're going to fetch the next instruction 10 cycles later, which kind of defeats our purpose, right? We want to fetch the next instruction in the next cycle. We don't want to wait for 10 cycles. Okay, so basically the simplest dynamic branch prediction techniques is last time predictor. Hopefully it's obvious what this means, right? Basically, the processor guesses that the branch will take the same direction as its last instance. Basically, you basically record what happened to the branch when it was executed the last time you saw the branch in the pipeline. And you can associate this information with a program counter clearly. And the next time you fetch that program counter, you're fetching an instruction from that program counter, you look up that bit saying what happened to that branch. If it says taken, you predict it as taken. If it says not taken, you predict the branch as not taken. Basically, that's the last time predictor. And this requires clearly a single bit per branch. It's stored in the branch target buffer, but it could be stored separately also, but it's indexed by the program counter, basically. You associate this last time prediction with a program counter. It indicates which direction the branch went last time it was executed. So if you actually look at this execution right now, the branch is for the first 10 executions is taken. For the remaining 10 executions, it's not taken. And assume that this is happening in a loop. Basically, the branch is always executed like this. 10 executions taken, 10 executions not taken, and then you execute something else in the program, and then you go back to the branch. 10 executions is going to be taken, 10 executions is not going to be taken, and then you execute some other stuff, and then you go back to this branch. Basically, this is repeated behavior. And if this is the repeated behavior, in the steady state, the parts that you would mispredict are whenever the current execution doesn't have the same outcome as the previous execution. For example, here, right, we're focusing on this taken and not taken over here. If whenever you predict in this instance, the previous instance was taken, you predict this instance as taken, but unfortunately, the branch turns out to be not taken, so you flush the pipeline. So this is where you mispredict. The second place you mispredict is when you go from this not taken to this taken. Basically, when you loop back, if you will, and you start executing the branch again. And in this instance, the branch will be predicted as not taken because the previous instance was not taken. Unfortunately, in this instance, the branch will be taken. So if you will flush the pipeline, so you make another mistake. So basically, you make 2 mistakes out of 20 executions, and that gives you 90% accuracy, 18 out of 20 correct guesses, which is much better than any static prediction mechanism that we saw, right? So 90% is quite good, as you can see over here. But we'll do better than this also later. So basically, if you look at this, if you think about this a little bit, this always mispredicts the last iteration and the first iteration of a loop branch. Think of this as a loop branch or something like that. This is not a loop branch, clearly, because there's a lot of not takens over here. But in a loop branch, you always predict the last iteration because last iteration is always, assume that the loop is most of the time taken, meaning you iterate in the loop. You always predict the last iteration, meaning last iteration is supposed to go not taken, but you predicted taken. And then the first iteration, when you come back to iterating the loop again, it's supposed to be taken, the branch is supposed to be taken, but you predicted not taken because the last instance was getting out of the loop, right? So basically, accuracy for a loop with n iterations is n-2 divided by n, always. So this is great for loop branches for loops with large n. So if n is 1 billion iterations, whenever you go into a loop, you iterate 1 billion times because you're adding two vectors, for example, with 1 billion elements. That's great. Your accuracy is almost 100%. Right? So as n goes to infinity, your accuracy approaches 100%. Okay, but unfortunately, loop branches for loops with small number of iterations is not that great. For example, this is a very worst case loop. You basically take the loop branch once, execute 1 iteration, and the second iteration, you exit the loop. You always execute 1 iteration in the loop. So the loop branch execution history looks like taken, not taken, taken, not taken, taken, not taken, taken, not taken. And if you always predict what you did last time, you'll always be wrong, clearly. This is 0% accuracy. If you can somehow recognize this, you can clearly make this 100% accuracy, right? The key is basically somehow recognizing it. And actually, we will talk about some mechanisms like branch confidence estimation if we get the time to do that. You can have a separate, let's say, meta predictor that examines your decisions and says, oh, I'm doing the wrong thing here. I'm getting 0% accuracy. Can I do better? Maybe I reverse the prediction, right? So if you have a confidence estimator that basically tells you how confident you are in this prediction, then you can actually reverse the prediction that you do over here. But that requires additional hardware. That's not last time predictor anymore. That's last time predictor augmented with a confidence estimator that reverses the prediction. But existing mechanisms can actually potentially do this clearly. Okay, so hopefully it's clear the benefits and downsides of last time predictor. How do you implement this? As I said, it could be implemented as a direction predictor over here, indexed by the program counter. It could be part of the branch target buffer as well. And this is an example where it's part of the branch target buffer, basically. So we will later cover caches. So exact structure of this will be very similar to caches. Don't worry about it right now. But basically, we're indexing a memory structure. And that memory structure is giving us the target address as well as the last time prediction, 1 bit per entry, whether taken or not taken. And we have a tag to make sure that we actually match the program counter completely because we have a limited size table over here. But this will become more clear when we talk about caches. Exact implementation of this will become more clear when we talk about caches 2 weeks later, essentially, or maybe 2+ weeks later. Okay, but basically this is also called a branch history table. This is the direction predictor. This branch history table entry is updated with the correct outcome after each execution of a branch. Okay, and that is a single bit. And that bit is essentially looks like this. It's a state machine, basically. You can think about it as a state machine, a single bit output. The single bit can be 0 or 1. I basically encapsulate them as predict not taken or predict taken. And if you predicted the branch is taken and it's actually taken, you stay in the state. But if it's actually not taken, you go back to, you go to some other state which says you should predict not taken, basically change the bit to 0, for example. And if you're predicting it not taken, and it's actually not taken when you actually executed the branch, you stay in the state. But if it's actually taken, you go back to the state. Okay. So one thing to recognize over here is that you change your mind very quickly. Basically, you can think of this as a belief system, right? You have some belief or evidence, let's say, based on some evidence. And you basically believe that this branch should be predicted taken. But if it's not taken, then you basically quickly say, oh, it should be predicted not taken now. You basically are changing your belief system very quickly. And this may not be very good because usually the branch behavior may not change immediately with one single opposing outcome. And we're going to improve on this that way. Basically, the problem we realized, or people have realized also in the 1960s and early 70s, etc., more in the 70s, and last time predictor changes its prediction from taken to not taken or not taken to taken too quickly with a single opposing outcome, even though the branch may be mostly taken or mostly not taken, right? So can we actually do better? And the idea is very simple over here. It's actually used in many, many engineering techniques. The idea is to add hysteresis to the predictor so that the prediction does not change on a single different outcome. It waits for some time to gather more evidence, basically. And if the evidence points that, oh, the branch is actually going to change behavior, then you actually change the prediction also. So you move a little bit slowly. You don't basically change your mind very quickly. And the idea is to use 2 bits to track the history of prediction for a branch instead of a single bit. So I'm going to talk about this, but let me give you an analogy. I like my favorite analogy for this is the air conditioning system. So in a room, you have an air conditioner, and your goal is to keep the air at 20 degrees Celsius. Okay, right now it's at 20 degrees Celsius. The temperature measurement is 20.2 degrees Celsius. Do you actually turn on the cooler or air conditioner at this point? Maybe you should wait for some time, right? Why? Because you turn on the air conditioner, the temperature becomes 19.9 degrees. Do you turn on the heater at that point? Right. Okay, let's assume that you turn on the heater right away by changing your mind quickly whenever the temperature drops above or below very little at the 20 degrees, around the 20 degrees. Then you basically keep oscillating, right? Then you keep switching on the heater and the cooler, heater and the cooler, heater and the cooler, heater and the cooler. And you never basically stop at a, let's say, stable interval. And people may become upset, clearly, if the heater and cooler are always working, not to mention that it's very energy inefficient. So the idea to fix this problem is to add hysteresis. And the hysteresis could be very simple. I'm going to wait. I'm not going to change or switch to cooling or heating based on a very small change or small deviation from 20 degrees. I'm going to wait until some point where I have enough evidence that the temperature is rising significantly or falling significantly. For example, I will wait until I make 3 measurements, and those 3 measurements say that the temperature is getting close to 21 degrees, right? You could actually use thresholding for this. And when you actually reach 21 degrees, then you actually enable the cooler. And similarly, on the other end, you could actually wait until you see 19 degrees, for example. So this is an example of hysteresis. And here, we're going to add the hysteresis using the state machine. Instead of having 1 bit whose outcome can be clearly changed quickly, we're going to have 2 bits. And we're going to have 2 states each for taken or not taken instead of 1 state for each. And this was proposed by the seminal paper by Jim Smith, which was actually the state of the art for about a decade after it was proposed, because this actually improved the performance significantly of last time prediction. This is called the 2-bit counter-based prediction. Essentially, each branch is associated with a 2-bit counter. 2 bits are not magic. It could be 3 bits. You can add hysteresis with any number of bits, as we will see. But even adding 1 more bit provides hysteresis. And also 2 bits are better than 3 bits in terms of hardware cost, clearly. But we will see later some mechanisms in real life employ 3 bits, for example. And the idea is to make sure that a strong prediction does not change with a 1 single different outcome. You wait for multiple opposing outcomes. This is also called bimodal prediction. I don't like the name that much, but it's also used in your in the McFarlane paper that I assigned to you. 2-bit counter prediction is actually nice, I think. But this is what the state machine looks like. And basically, we're going to have 2 states where we will predict the branch as taken, and 2 states where we will predict the branch as not taken. If you're in this state, and basically we're going to have a counter, and this is a 2-bit counter. This counter uses saturating arithmetic. Basically, there's a maximum value and a minimum value. Maximum value is 3, minimum value is 0. And if you actually saturate at that value, Basically, you cannot increment beyond those values or decrement beyond those values, essentially, or increment or decrement beyond the maximum and minimum values, respectively, let's say. So you have two states. One is the state which you're predicting as taken. If the branch is actually taken, you basically keep in this state. This is saturated. But if the branch is actually not taken, the next state is that you still predict the branch is taken. But this is a weakly taken state, because if you see the actually not taken outcome again, then you switch to predicted not taken, as you can see in the next instance of the branch. And if you see another actually not taken outcome again, you switch to a strongly predicted not taken state, which requires two opposing outcomes to get out of that prediction, basically. That's the idea, basically. You have a 4-bit or 2-bit state machine with 4 states, and there's some strong states. And if you're in strong states, strongly taken or strongly not taken states, you're strong in your belief that this branch should be predicted taken. So your belief does not change with a single opposing outcome. It requires 2 opposing outcomes to change your belief and your prediction accordingly. Okay, so hopefully this is simple, and that's an interesting idea. And you can actually follow this on your own. It's very simple, actually. It's 2-bit counter. But the idea is to change the prediction after 2 consecutive mistakes if you're in the strongly taken states. If you're in the strong prediction state, strongly taken or strongly not taken. But if you're in the weakly taken states, one opposing outcome changes the prediction, because presumably you haven't made up your mind yet as to whether this is strongly taken or strongly not taken, right? That's the idea. Okay. So if there are any questions, feel free to ask. This is actually very simple also. Each branch is associated with now not a single bit counter, 2-bit counter. There's a little bit more hardware cost. 1 more bit provides a hysteresis. And as we said, a strong prediction does not change with a single different outcome. Let's take a look at some examples. So accuracy for a loop, sorry about that. Accuracy for a loop with n iterations, in this particular case, it becomes n-1 divided by n. Why? Because you only mispredict the loop exit branch. So you have a loop. You have some, whenever you're exiting the loop, the loop branch is always not taken, right? Almost always not taken, except when you're exiting the loop. When you're exiting the loop, you mispredict the branch for sure, because all of the prior history is taken. So you're strongly taken when you're exiting the loop. So you predict it as taken, but the branch is not taken. You mispredict it. Now you go to the weakly taken state. The next time you enter the loop and start executing the loop branch, it's going to be taken, and you predict it as taken, because you did not change your mind based on the loop exit that you have done. When you enter the loop, you're going to predict the branch as taken again. So this saves you 1 misprediction. Before, with the last time prediction, you get n-2 divided by n, if you remember. And as a result, here you get 95% accuracy. If you remember the last time predictor, it was 90% accuracy. And that 5% makes a big difference, actually. If you look at this, let's say, not so... the branch that we did not do so well on, here you get 50% accuracy still. Basically, sorry, in last time prediction would get 0% accuracy over here, but here we get 50% accuracy with 2-bit counter prediction, assuming that the counter is initialized the weakly taken. If you are weakly taken, you would always predict the taken ones correctly, and you would always mispredict the next not taken executions. So 50% is better than 0% clearly. But we will see that there are better ways of dealing with this branch later on. Okay, so basically the takeaway of this hysteresis-based 2-bit counter-based prediction is you get better prediction accuracy, but more hardware cost. Again, the counter can be part of a BTB entry. And as I said, you could generalize this to 3-bit counters, 4-bit counters. It depends on the behavior of the branches. And the state transitions don't need to be exactly symmetric, as I showed you over there. The stability depends on the behavior of branches. And people have done a lot of interesting studies. As I said, existing processors can use 2-bit or 3-bit counters, but also 1-bit counters sometimes for easy to predict branches. Okay, now I'll ask you the question, is this good enough? And probably the answer would be not good enough, right? Basically, with 2-bit counter prediction in 1980s, when it was invented, you get 85 to 90% accuracy on the programs of that day. That sounds great, but that's not good enough. Basically, the branch problem is quite big. So if you go back to the example that I showed you, 90% accuracy is not good enough, right? It still leads to 200% extra instructions fetched, and your IPC is 3x lower than a perfect IPC, perfect prediction IPC. 85% is even worse. As you can see, your IPC is 1.25 as opposed to a 5. 80% is even worse. So basically, there's a need to improve the branch prediction, because even 90% is not enough. Even 95% is not enough if you actually keep increasing the depth of the pipeline and width of the pipeline. That's why people started developing even more aggressive techniques. And we're going to see the idea of 2-level prediction right now. Okay, I'll keep going unless you interrupt me. If I hear any sounds, feel free to ask questions. And you can ask questions on Zoom also. Okay, so two-level prediction is exciting. It was introduced by this work in Micro 1991, 10 years later than the Jim Smith's paper that we briefly discussed, as you can see. And this realizes something very, very interesting. And this is the fact that predictability has other dimensions in terms of the program behavior. So last time and 2-bit counter predictors exploit last time predictability. But we need to look at another dimension also if you really want to improve branch prediction accuracy. Meaning, the first realization is that a branch's outcome can be correlated with other branches' outcomes, completely independent branches, independent in the sense that they're in some other program counter. But they may be dependent on each other in terms of some semantic relationship of the program, right? This is called global branch correlation, and we're going to look at that first. And the second realization is that a branch's outcome can be correlated with past outcomes of the same branch, other than the outcome of the branch last time it was executed. So this is different from the last time predictability, but the same branch can have a long history of execution. And based on that history of execution, you can gather some patterns of execution. Like loop branches, for example, may have this information. If a loop always iterates, let's say, 16 times, with a history that takes into account those 16 times, you can actually predict that loop perfectly, right? Whereas last time and 2-bit counter predictors are not able to predict that loop. And this is called local branch correlation. So we're going to look at both, and both are employed in existing processors, actually. This actually made a huge breakthrough in the design of branch prediction mechanisms in microprocessors. And these are implemented in essentially all processors today. So let's take a look at the first one. So this is global branch correlation. The idea is very simple. Recently executed branch outcomes in the execution path are correlated with the outcome of the next branch. And this is best understood by looking at code like this. Probably you've written code like this. And if I tell you this code, the first branch tests condition 1, the second branch tests condition 1 and condition 2. Just by looking at the semantic relationship of the predicates of the branches, you can say there's some correlation here, right? If the first branch is not taken, then second is definitely not taken as well. So there's some correlation clearly. It's not perfect because if the first branch is taken, you don't know whether the second branch will be taken because the second branch tests another condition. But if you know that the first branch is not taken, you know that the second branch is also going to be not taken. So if you can capture this correlation in your history somehow, then you can actually predict the second branch much more accurately. Okay, other examples. If x is less than 1, you do something. If x is greater than 1, you do something else. These are two different branches. And here, another dependency exists. If condition 1 is true, A is set to 2. And then another branch tests if A is equal to 0. Right? Clearly, there are patterns here. If the first branch is taken, second is definitely not taken in both cases. Again, if the first branch is not taken, you don't know. But if the first branch is taken, you know second is definitely not taken. Right? So that sounds good. When I said you don't know, you don't necessarily know, potentially, right? Maybe there are some other things in the program that also correlates. So these are clear examples of correlation across different branches in a program. Another one here. If condition 2 branches consecutively test condition 1 and condition 2, the next one tests both condition 1 and condition 2. In this particular case, if the first and second branches, Y and Z, are both taken, then X is also taken. Last one is also taken. If Y or Z is not taken, then X is also not taken. You can think about this a little bit, but clearly there's very interesting correlation here. And this is a very famous program. This is a program that was designed in SPEC. SPEC is the Standard Performance Evaluation Corporation. It basically releases workloads, benchmarks, with which microprocessors are evaluated against. So everybody tries to maximize their spec marks, for example, to sell their microprocessors. And at the time in 1992, this was a very hard program. It's called equation to truth table. It generates truth table based on a Boolean expression. And you can see that it has some branches like this. So if A is equal to 2, you set AA to 0. If BB is equal to 2, you set BB to 0. And then you check if AA is not equal to BB. In this particular case, you can analyze the program and you can see that if B1 is taken and B2 is taken, then B3 is not taken. And all of the machines that had last time predictors or 2-bit counter predictors did not do well. But the machines that had global predictors that could exploit this correlation between the branches did very well on this one. So much so that this workload became not so interesting anymore. Meaning, if you had a global branch predictor, this workload was easy workload. So this is an example of improvements in hardware making a particular workload much faster. As a result, workload becomes not so interesting anymore. So they actually removed this from the performance evaluation suites going into the future because they said that it's basically not that interesting, assuming you implement the state-of-the-art branch prediction mechanisms. Okay, so I've given you some intuition as to global branch correlation. Now let's talk about how to capture it. Capturing it is actually not that hard. We're going to have another level of history, which is going to be called the global history register or global register in your reading. We associate branch outcomes with global taken, not taken history of all branches. So we make a prediction based on the outcome of the branch the last time the same global branch history was encountered. And global branch history is a bit vector, basically. It encodes the last taken, not taken history of last n branches. For example, n could be equal to 4. You encode the taken, not taken history of last 4 branches. It's a 4-bit history register. And each of them, each bit is a 1 or 0. 1 can be taken, 0 can be not taken. And that's the history that you see in the last 4 branches that you have executed. Okay, that's about implementation, basically. You keep track of the global taken, not taken history of all branches in a register. All branches meaning, of course, it's a limited register, right? 4 bits, 16 bits. Existing system has 16 bits, but we will see that people have improved this in different ways. So you can actually go to 500 bits, 124 bits, 1024 bits in existing systems in a predictor called Tage, which we will see hopefully at the end. So you have this global history register, and you use this global history register to index into a table that recorded the outcome that was seen for that global history register value in the past. This is called the pattern history table. It's essentially a table of 2-bit counters, but it doesn't have to be 2-bit. It could be 1-bit. If it's 1-bit, it's a last time global history predictor, meaning if the global history that I see is like this, what happened to the branch last time? Was it taken or not taken? And you can clearly have 2 bits over here, so that you can have a 2-bit state machine. You can have basically you can employ the you don't change your mind immediately based on hysteresis, right? So I'm going to show you a picture of this. So this is called the global history or global branch predictor. It uses, the reason it's 2-level predictor is it uses 2 levels of history. One is the global history register, and the other is history at that global history register. What happened last time I saw this history of branches? Was the branch taken or not taken, or strongly taken or weakly taken, or strongly not taken or weakly not taken, right? If it's 2-bit history. And it looks like this, basically. It's very simple. As I said, the first level is the global branch history register, or m bits. This is the direction last n bits, last n branches went, encoded with a single bit per branch. You can see it could be 16 bits, for example. Then the pattern history table is 2 to the 16 entries. The second level is this pattern history table. Sorry about that. This is a table of saturating counters for each history entry. This is the direction the branch took the last time the same history was seen, observed by the processor. And you can see the global history register looks like this. It basically encodes the last bit over here is the youngest bit, meaning this is the immediately previous branch's direction. The next one is the previous branches. And if you go back in the history, this is the 16th previous branch's execution. Basically, you keep adding to this history register as you execute the branches. Okay, because you know the outcomes when you execute the branches, right? And then you index using this history and basically check what was the outcome of a branch when I last saw this history. And if it's taken, you predict the branch is taken. If it's not taken, you predict the branch is not taken. Okay, so you can see the implementation is relatively simple, but more complicated than prior mechanisms. And each entry could be a 2-bit counter, but also a 1-bit counter, also 3-bit counters, as we discussed. Let me give you a quick intuitive example as to why this works. I would recommend reading the Combining Branch Predictors paper from McFarling, because it actually has a nice explanation. Gshare is the global history register, and it basically uses a 4-bit history register. And we're going to look at this nested loop over here. I'll go through this relatively quickly. I'd recommend you take a look at the paper, but let's take a look at this last one. So last one actually is the branch that tests I. And you can see that this iterates for a long time, meaning it's usually taken. But the global history you see when you fetch this branch is 1110. Why? Because last 3 branches are the last executed by, these are the branches that test J. And you can see that this loop iterates 3 times, right? The first time, basically, the last time it iterates, it's not, the loop branch is not taken. The previous time is taken. The previous time is taken, and the earlier branch is really the I branch over here. It's mostly taken, basically. So the history of this branch that tests I, the history at the time you test this branch I, last 3 branches actually test J, and the history looks like this: taken, 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 not taken. And you predict I as taken because it's supposed to be taken. Over time, you do the training of the predictor, and it's predicted as taken. And the next history is you shift in the outcome of I, which is going to be taken, and you shift out the oldest outcome from here. So the next history becomes taken, taken, not taken, taken, which is this one over here, as you can see. You shift in the last outcome, you shift out the oldest outcome. And the next branch you encounter is really testing whether J is less than 3, and it's going to be taken. So whenever you see taken, taken, not taken, taken history, the outcome is always going to be taken, because as you can see, this is a static loop over here. And then you shift in the new outcome, you shift out the oldest one. The next one, it becomes taken, not taken, taken, taken. That's your history. And whenever you see that history, again, this is taken. So basically, if you actually go through and simulate this program, you will see that whenever the global history register is this, the result is taken. Whenever the global history register is this, the result is taken. Whenever it's this, the result is not taken. And whenever it's this, the result is usually taken. So now you're actually kind of representing what happens in the program based on this history register and the associated result that the branch should have. And I think this is very powerful. I recommend you take a look at the paper and examine this in more detail on your own time. It's a very good explanation of global history and why it works. Okay, let me give an example of this global history register, and then we will take a break for 10 minutes. Basically, Intel Pentium Pro had this 2-level global branch predictor, and it was very important for them. It had a 4-bit global history register, just like the last example that we saw. It had multiple pattern history tables of 2-bit counters. Which pattern history table to use is determined by the lower order bits of the branch address. So they actually incorporated the branch address to select which pattern history table to use. But its global history register doesn't have information about program counter, right? It's just the global history of last 4 branches. And the reason they had this was because this was a very aggressive processor. It had out-of-order execution, superscalar execution, precise exceptions using reorder buffer, and branch prediction was extremely important for them. And this 2-level branch predictor actually improved the performance significantly. And it was a major contributor for it being the first widely commercially successful out-of-order execution machine, which is really the, let's say, grandfather or grandmother of existing CPUs, I would say. Okay, and this is what you have seen in earlier lectures also. Basically, before I take a break, I've given you the intuition as to why this works, but there are actually beautiful works that explain why this really works by examining different semantic relationships to the programs. And if you're really interested, I'd recommend this paper that talks about the correlation and predictability of the branches. And it actually has very interesting, rigorous analysis. It basically says that usually there are 3 branches, 3 past branches that matter for the prediction of this particular branch. Unfortunately, you don't know what those 3 branches are. It could be anywhere in the history. So you construct, for example, a 1024 entry history. You look back 1024 branches for a particular branch. Branches at history 1000, 885, and 3 could be the important ones. For another branch, it could be totally different 3 branches. But usually 3 branches matter for predictability. If you get those 3 branches right, then you can actually predict the branch very, very accurately. Now, we will see later the Perceptron branch predictor that tries to find the correlations of different branches. And the idea it will have is to try to find the correlations such that it would get those branches that are going to affect the most the current branch that we're trying to predict. So I find this fascinating. So later people actually developed mechanisms using machine learning to try to get this correlation right. Okay, this is a great place to stop. I will take a break for 10 minutes, so 2 minutes after the bell. And we will continue very briefly on global branch predictor and then move on to local branch predictors and more sophisticated mechanisms. And feel free to ask questions in the chat or get your questions ready in the meantime. Okay, I think we can get started. Let me see. Let me remove this here. Okay, so this is where we left off. We were talking about global branch prediction, and we actually started. Now let's talk about how to improve it, actually. So global branch predictors are actually quite accurate, and they were implemented in Pentium Pro, and that made a big difference actually at that time. But we can improve their accuracy. So if the way we describe the global branch predictor, it uses only the global history register to make a decision about a branch. So it doesn't even use the program counter of the branch, right? In Pentium Pro, actually, they used the program counter to distinguish, to index into different pattern history tables based on the program counter. So you added some more context information in Pentium Pro. And there are different ways of adding context information to take into account which branch is being predicted. And that's the idea, basically. If you add more context information and supplement the global history register with that context information, we can actually make a better prediction. And this is one way of adding more context information. It was actually introduced by the paper that I assigned to you, the combining branch predictors paper, and it actually had a huge impact also. It's called the Gshare predictor. You have the global history register and you hash it with the branch PC. Basically, you have the branch program counter and branch history register. It's called the global history register, actually, in this particular case. You XOR them or use some other hash function, and you use that hash function to index the pattern history table. Now, you don't only take into account the branch history information, global history information, but also the branch context, meaning what program counter am I using? And this distinguishes the history for different branches. This is actually interesting. You don't have to hash the entire branch address. You could actually hash parts of the branch address. You could actually hash a bigger context in the program. Some people have looked at using the current call stack information in the program. So basically, there are other context information that you can use, but Gshare has been extremely popular. And the key benefit is more context information improves the accuracy of the prediction because you have a little bit more refinement as to how you're predicting a given branch. And it also leads to better utilization of the 2-bit counter array. So this is actually interesting because if you don't have hashing to index your pattern history table, meaning 2-bit counters, some counters may be overly used, let's say, where some counters may not be very much used. Now, by hashing, you're really distributing the usage across many counters in your pattern history table. This is, in general, an issue with hash tables, for example, right? Whenever you're using hash tables, you want to balance the distribution of things in the buckets, and we have the same problem over here. And that better utilization also leads to better prediction accuracy because things don't interfere with each other as much in the pattern history table. Okay, the downside, of course, is as you keep adding more context information, you increase the latency. In this particular case, it's just XOR. But if you keep adding more XORs, for example, more information, your latency starts increasing. And this could already be a critical path in your pipeline. Okay, let me finish the global branch predictor. So remember, this was our picture of the one-level branch predictor. You have the program counter, you index the BTB, you get the target address, and you index the direction predictor that tells you whether something is taken or not taken using the program counter. With the 2-level global history branch predictor, we use a program counter to get the target address. We use the global branch history register to get, which encodes which direction earlier branches went, to get the direction prediction. Okay, and this is very simple, as you can see. With Gshare, more context information, you use the program counter to get the target address because target address is only a function of the program counter, clearly. But you use the program counter information as well as which direction earlier branches went in a hashed way to actually get the direction prediction. So you get more information basically that way. And also you get better utilization of the direction predictor entries. So just to give you an idea, if your global history register is 16 bits, your direction prediction can be 2 to the 16 entries. Each of them can be 2-bit counters. If your global branch history is, let's say, 2 to the 24 bits, your direction prediction can be 2 to the 24 entries, right? Better utilizing those entries could be useful. Okay, so that was the global branch correlation. Now let's look at the second realization, which brings us to local branch correlation. And this realization is that a branch's outcome can be correlated with past outcomes of the same branch, in addition to the outcome of the branch that is exploited by the last time predictors. And this is again nicely explained by your paper, Combining Branch Predictors. And if you look at this nice single loop over here, well, clearly it's a very easy loop. I'm going to read it from here, actually. If the loop test is done at the end of the body, the corresponding branch will execute the pattern 1, 1, 1, 0 to the n times, which is where 1 and 0 represent taken and not taken respectively. And n is the number of times the loop is executed. You don't execute this loop once, you go back to this loop because there's an outer loop that brings you back to this inner loop, right? Clearly, if we knew the direction this branch had gone on the previous 3 executions, then we could always be able to predict the next branch direction. That's the idea, basically. You always repeat the same pattern in this loop, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. And every time you execute the loop branch, you have a different pattern that's repeated, that's shifted in and shifted out based on which particular instance you're in. And if your previous 3 branches are 1, 1, 1, your branch should be predicted as 0, meaning you would exit the loop, right? That's the idea over here. Okay. And this is also described in the paper. Basically, to predict the loop branch perfectly, we want to identify the last iteration of the loop somehow. By having a separate pattern history table entry for each local history, we can distinguish different iterations of a loop. Because whenever this branch is executing, you kind of have different histories that the branch sees. So sometimes it's 0, 1, 1, 1, sometimes it's 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0. And if it's an instance of the branch inside the loop, it's going to be taken. If it's an instance of the branch that will get out of the loop, basically, the branch will be predicted not taken. And keeping track of the local history of the branch will tell you that the branch should be predicted not taken if the prior 3 instances are 1, 1, 1, meaning they're taken. And the previous one was not taken, as you can see over here. Yeah. Okay. So hopefully this is clear. Basically, you keep track of the pattern of where this particular branch went, and each pattern leads you to a different entry, different prediction, basically. And you train those predictors differently because it's based on the history that you've seen last, not just the PC program counter anymore. Okay, so how do you capture this in real life? And the idea is to have a per branch history register. Based on a program counter, you have a history register. This is a local history register, just looks at the local history of that branch. And you associate the predicted outcome of a branch with the taken, not taken history of that same branch, of that very same branch. You basically keep track of what happened to the execution of this particular branch at program counter X. And you make a prediction based on the outcome of the branch the last time the same local branch history was encountered. This is called the local history or local branch predictor. It uses 2 levels of history again, right? Not 1 level. One is the per branch history register. What's the local history of the branch? And the second is history at that history register value, meaning what was the outcome of the branch last time I saw this history for this branch? Was it taken? Was it not taken? Was it weakly taken? Was it weakly not taken? So basically, you can have hysteresis in this one as well, right? So that's the idea. So the picture is very similar to the global branch predictor. As you can see, there are 2 levels. One is here on the left. You have local history registers. Basically, the first level is a set of local history registers. Each history register is of n bits each. And you select the history register based on the program counter of the branch. So based on the program counter, you choose one local history register. And then you index a second level table. It could be multiple tables also. It could be separate tables for the branch also. So there is actually a design choice over here. In this case, I show a single pattern history table, but there could be multiple pattern history tables based on the program counter of the branch. And this is essentially a table of saturating counters for each history entry, meaning whenever I saw this history, local history, where did this branch go? The direction the branch took last time, the same history was seen, as you can see over here. And that's basically, again, these could be 2-bit counters, 1-bit counters, 3-bit counters, depends on the hysteresis you want to add. And you can see that this is simple, but it's less simple compared to, or more complex compared to the global global branch predictor, because global has only one history register, which is the global history register, if you remember. Now we have local history register per branch. Okay, so this is how we integrate into the pipeline. Basically, we have this program counter. We index the local history registers, table of local history registers, using the program counter. We get the local history for this branch at that program counter. And then we index the direction predictor. Again, the direction predictor can have multiple pattern history tables, but it could have a single pattern history table also. Now, there are trade-offs associated with it, because if you have a single pattern history table, different branches may interfere with each other in this pattern history table, which kind of goes against the local prediction idea, but it's simpler in terms of hardware, clearly, because these are actually costly structures, right? If your history is, for example, if your local history is 24 bits, then you have 2 to the 24 entries. Each of them is 2 bits. Then you have 2 to the 25 bits over here, which is 2 to the 22 bytes. Now you can imagine that that's 4 megabytes, right? I think, yes, 2 to the 22 bytes, right? So that's a lot, actually. It's a huge table, basically. If you replicate it for 10 different branches, 10 different program counter sets, let's say, that's 40 megabytes already. And you don't want that. idea. That's why people actually need to make a trade-off in terms of the accuracy of the prediction and the cost of the predictor. Right? If having a single pattern history table is acceptable in terms of the accuracy degradation, you will get, as opposed to having many history tables, you basically can get that accuracy degradation while saving a lot of hardware cost. Okay, so basically that's the local history branch prediction. Oh, as I said, each of these local histories show which directions early instances of this branch at this program counter went. Okay, I'm not going to go into the details of this, but there's a design space over here. There's actually this beautiful paper that introduced the two-level branch prediction, has a categorization of the design space. For example, the branch register can be global. It could be per set of branches or per branch. Per branch is clearly unreasonable, right? Because a program can have millions of branches. Are you going to dedicate 1 million tables? No, usually it's per set of branches or global. Pattern history table counters can be adaptive or static, meaning adaptive is basically it's 1-bit or 2-bit or 3-bit counters. Static means compiler says what should be the pattern history table value, right? This is very similar to the predictions that we saw earlier. Compiler can also provide profiling information potentially. It's not good in general, but it can. And the pattern history table can be global, meaning shared by all branches, or it could be per set of branches or per branch. Usually per branch components are very expensive, but if it's global, it's cheap, but the accuracy may not be great because you may have a lot of interference in the global tables. Okay, I'd recommend you take a look at works like this that actually nicely formalize the space. Of course, in this course, we're never satisfied, right? And in real life, it's good to not be ever satisfied so that you can actually improve. You can always get to a better place, right? If you said at some point, oh, okay, this branch prediction accuracy is enough for us, we would never reach the newer heights that we have examined. And the question is always, can we do better? And we're going to see how we can do better. If there are any questions, again, feel free to ask. I hope people are following, but you can stop me by asking questions. Okay, but basically, let me give you multiple ideas. One is the fact that predictability of branches varies. Some branches are more predictable using local history. Some branches are more predictable using global history. For others, a small 2-bit counter is enough. Yet others, just a single bit is enough. Yet others, a single basically compile time prediction is enough, because some branches are actually extremely easy to predict because 100% of the time almost they go one way, taken or not taken. So this actually shows that there's heterogeneity in the behavior, predictability behavior of branches. And whenever you see this, whenever there's some heterogeneity, you should always think, if I design a mechanism that tries to basically treat everything the same, it will not work because it's not heterogeneous. No, basically there's no one-size-fits-all branch prediction algorithm for all branches because all branches are different. And this is a very fundamental thinking in a sense, basically. You're trying to homogeneously treat a class of items that are by nature very heterogeneous. Every branch cannot be predicted with a global branch predictor accurately. Every branch cannot be predicted with a local branch predictor accurately. Every branch cannot be predicted with a last time predictor accurately. But different branches can almost perfectly be predicted by these different predictors. So the idea is, why not exploit heterogeneity in behavior of branches by designing heterogeneous or hybrid branch predictors? And this was first proposed by the paper that you're reading, also combining branch predictors. And the idea is very simple, basically. The philosophy is, again, very general, right? It can apply to many things in life, many design decisions. You can have heterogeneous processor cores, for example, to execute different workloads, which already exist, actually. If you look at latest processors, they have different types of processor cores so that they can execute different types of workloads. And now we have different types of branch predictors. We use more than one type of predictor, in other words, multiple algorithms, and select the best prediction for a given branch or for a given history. That now becomes a design choice, right? For example, we can have a hybrid of 2-bit counters and a global predictor. We can have a hybrid of global predictor, local predictor, and 2-bit counters. We can have a hybrid of 10 different predictors. As we will see later, we're going toward that in existing processors, basically. Clearly, there are advantages and disadvantages. We get better accuracy. Different predictors are better for different branches. But we also get another advantage that we did not talk about much before, which is the warm-up time. Meaning, if you have long histories, it takes a long time to warm up the predictor so that you can start predicting accurately. For example, if your history register length is 24, you need to see a lot of patterns for that particular branch so that you can warm up a lot of counters. Well, not for that, for different histories, so that you can warm up a lot of counters. So it takes some time for these predictors to get trained, let's say. This is also called training time, but it's not a learning approach, so I don't want to use the word training. It's really warm-up time. You're warming up so that you can do good predictions. But some other predictors warm up very fast. For example, a single bit supplied by the compiler. You don't need a warm-up, right? You have that bit, you predict. There's nothing to warm up on because that bit is already supplied to you, okay? So basically, different predictors have different warm-up times. If you actually have hybrid predictors, while one predictor is warming up, one more accurate predictor is warming up, you can use a less accurate predictor to predict the branch, and you can do at least reasonably, as opposed to doing nothing, right? So this is actually a very important upside of heterogeneity as well, warm-up. Of course, there are disadvantages, which is clearly more hardware cost, more complexity, longer access latency, as we will also see. But you also need another decision to make right now. If you have hybrid branch predictors, how do you select which predictor to use for your current prediction? And this is called a meta predictor or selector. Okay, there are many ways of designing the selector also. We're not going to go into. It can use information similar to or somewhat different from the information that we included in our predictors so far. But let me give you an example. This is the first machine that has implemented this hybrid branch predictor idea. It is implemented in actually all machines today, all high performance processors today. It's essentially all processors that you're using in your phones, for example. This is Alpha 21264. It's a beautiful processor, and I actually recommended this paper, Alpha 21264 microprocessor, which touches upon a lot of things that we have discussed in this lecture: out of order execution, branch prediction, scheduling, etc. And it also touches upon caches that we will cover later on. But if you look at this, it has a global predictor over here that uses a 12-bit global history over here, and each entry in the pattern history table is 2 bits. It supplies a global prediction. And then there's a local history table, which is indexed by the program counter. You get the local history. Each history is 10 bits, and you have 1,024 of these local histories, as you can see. And you index a pattern history table that is of 3 bits. So it's 2 to the 10 entries and 3 bits. Here it's 2 to the 12 entries, and each of them is 2 bits. You can see that the hysteresis, they decided it's 3 bits. They don't exactly describe how they update these 3 bits, but that's how it is. So you get a local prediction out of the local predictor, a global prediction out of the global predictor. How do you do that? You have a choice predictor, basically. How do you select? There's a choice predictor that acts on the global history, and that basically keeps track of which predictor was doing better the last time this global history was encountered with some hysteresis again. And based on that, it chooses either the local predictor or the global predictor and makes the final prediction. In this machine, this was important. The minimal branch penalty was 7 cycles. Typical branch penalty was much longer because of out-of-order execution. And the target addresses was stored in the I cache, instruction cache. This is basically branch target buffer was part of the instruction cache. And they reset the predictor tables on a context switch also. So there are actually a lot of other interesting things in branch prediction. What happens if you get a context switch? Do you keep the tables or do you reset them? And people actually study these interesting operating system and system level effects as well. But as I said, this is the first instance of a hybrid branch predictor in real life. This is 1990s, late 1990s. Now we're actually building up to 2020s slowly. And all machines actually have hybrid branch predictors today, as we will see. Okay, let me give you another idea. This is actually not news in a sense, because we talked about this earlier, yesterday also. Most branches are basically biased. Many branches are biased in one direction. They're either 99% or higher taken or not taken. Usually taken though, because most branches are loop branches. And if the loop is iterating many, many times, these are very biased branches. The problem is, actually, there's good news and bad news. If you actually use these biased branches, and if you actually use a very sophisticated predictor to try to predict them, what they do is they pollute the branch prediction structures, meaning they make the prediction of other, much more difficult to predict branches difficult by updating these counters in ways that these other branches do not like to be updated for better prediction, right? So basically, they cause interference in these branch prediction tables and history registers. The idea is, why not predict them in a much simple way? Meaning detect such biased branches and predict them with a much simpler predictor, like last time predictor or static predictor. The question is, of course, how do you detect them? But you can have basically simple counters that look at the prediction accuracy of the branches. And if it's very highly predictable, or the bias of the branches, if it's very highly biased towards taken or not taken, then you basically use a much simpler predictor. This is called branch filtering or branch classification, if you will. And this greatly improves performance by, again, introducing heterogeneity into the prediction. Branches that do not require difficult, let's say, sophisticated predictors, don't use sophisticated predictors for them. let use the resources, like critical resources of sophisticated prediction, only for those very difficult to predict branches. And I think this makes sense clearly, but this is a very good guiding principle as well. And this also introduces heterogeneity, basically. And again, heterogeneity is caused by the behavior of the branches. Okay, so, and then we asked the question, are we done with branch prediction? Hybrid branch predictors actually are quite well. At the time they were introduced, there were papers like McFarlane's paper showed 90 to 97% prediction accuracy on average. But as you know by now, 90% is not enough, right? And again, programs change. Today, we have a lot of very irregular programs. Machine learning in parts can be that way, training especially. Graph analytics, actually the graph structures, we have a lot of graphs that we're dealing with today in machine learning, genomics, etc. And these have very data-dependent traversal patterns in the graph. And as a result, getting to 90% or higher prediction accuracies is difficult, even with hybrid branch predictors. But yeah, basically that's the point. Difficult workloads still suffer a lot, and difficult workloads are increasing. For example, I'm taking an example from McFarlane's paper. GCC is a compiler, very heavily used, very successful. Its maximum IPC, instruction per cycle, with tournament prediction, which is the alpha 21264 predictor, is 9. So this is based on some theoretical studies. Basically, if you have a perfect machine with perfect resources, and if branch predictor was your only limiter, what is the maximum IPC you would obtain? You have a lot of resources, so you're not bound by execution units or fetch width, for example, but you're bound by branch prediction. So 9 is not bad, assuming you can achieve it, of course. But with perfect prediction, meaning 100% accurate prediction, maximum IPC goes by 4x. Meaning, even with tournament prediction, which is 90 to 97% accurate, we're not there yet. We're not exploiting the parallelism that's present in the program. So we will always ask the question, can we do better, basically, until we get very close to 100%. Okay, so now we're going to switch to some other branch predictor types that improve prediction accuracy by exploiting different things. One thing that I will talk about is loop branch prediction, detection and prediction. So people have over time figured out that loop branches that are predictable can be filtered out as well. Meaning you can actually count the loop iterations, detect the loop iterations, and if the loop iterations are actually constant across executions of the same loop branch, you remember what the loop iteration count was and predict the branch with that loop iteration. And this works well with small number of iterations where iteration count is predictable. Of course, this is used in Intel Pentium M, which is early 2000s, basically 2003, 2004, 2005, I think, or a bit later also 2006. And this actually made a difference in loop heavy programs that are with small loops. For example, hash tables have a lot of loops, right? Hash table based programs. Now you can actually improve this by having more information from the software. The software can also provide supply the iteration count. I'm not sure if they did this in this particular machine or new incarnations, but software can have more information about how long a loop can potentially iterate if you know the loop iteration count, if it's set at the beginning of a loop, for example, right? It doesn't need to be static. It can be set dynamically, right? So you can improve this one. I'm going to show that in a little bit, very briefly. We're going to talk about an exciting idea, Perceptron branch predictor. The idea is to use machine learning to learn the direction correlations between individual branches. And we're going to talk about that. And this is also used in existing processors. And the last one we will talk about is hybrid history length branch predictors. And the idea is here, don't have a single history length. Use many different history lengths because different branches are predictable, better predictable with different history lengths. Because some of them are not correlated with many branches. Some of them are correlated with many branches. So why not use different history lengths and different prediction tables? And this is also employed in existing processors. Okay, so very quickly, this is actually from a paper that was written by Intel that introduced the Intel Pentium M processor. You can see that there's a loop branch predictor over here. It basically determines where there's a limit, meaning the iteration counts. Assuming you determine the iteration count based on past executions or based on software information, you basically count how many times you executed this branch. And until you reach the limit, you predict the branch as taken. Once you reach the limit, you predict the branch as not taken. So that's the idea, basically. And you have a loop detector logic for this purpose as well. And then there are indirect branches, jump branch predictors. And indirect branches tend to, we're not going to talk about them in detail. I have some backup slides related to them, and we will not have time to cover them. But indirect branches are interesting because you don't predict a condition here. There's no direction prediction. There's a direct target prediction. But an indirect branch can have hundreds of targets potentially. And here, they basically have, you can basically use similar ideas like global history and differentiate between the different targets that an indirect branch will take based on the history of branches that you have executed so far. Again, the basic idea of global history is very similar, except you use the global history to decide which target to use from a branch target buffer, indirect branch target buffer in this particular case. Okay, and Intel Pentium M was introduced in 2003, and I will point you that advanced branch prediction was a good chunk of the die, as you can see. At that time, caches were not that big. It's 1 megabyte. 1 megabyte is actually pretty big for that time, but you can see that the branch prediction logic is occupying a good chunk of the die area over here. And you can also see that it's only 77 million transistors. This is less than 20 years ago. Today, we're at billion transistors and higher. Right? Okay, that brings me to more advanced branch prediction that's employed in the state of the art. And we're going to talk about a little bit about machine learning. How many people learned about perceptrons? I cannot see the hands very well. Has anyone learned about perceptrons? I don't know. Maybe you can raise your hand. That's the downside of this machine. I cannot see. Maybe it's because I'm highlighted. I cannot see you in the, let's say, large picture. But perceptron is a very, very basic neural network. I don't want to call it a neural network, in fact. It's really a single neuron. It's a simplified model of a biological neuron. It's a single layer network. Maybe that's the best way to actually specify it. It was developed in 1958 by Rosenblatt. And this book that he has written actually has a lot of great information about initial ideas of how to model biological neurons. And the idea was to actually make decisions just like a simple neuron. And a simple neuron is actually also a simple binary classifier. And we're going to model the perceptron as a binary classifier. Basically, it maps an input vector X. Input vector has some information, some n elements. So we call it X. And it maps this to a 0 or 1. Basically, it's classifying whatever it's seen to a 0 or 1. Or 0 can represent a cat or a dog, for example. A cat or not cat, clearly, right? That's what neural networks were used nicely initially, for example. So input is a vector X, vector of values X. Perceptron learns a linear function, if one exists, of how each element of the vector affects the output. And this is stored in an internal weight vector. So this is the training phase. Basically, you train the perceptron to get a set of weights. And these weights indicate how each element is correlated with the output. Each position in the element, basically each element you supply in the vector is correlated with the output. So you learn these weights across many different training samples. And whenever you want to make an inference, meaning classification, you get the input vector, you multiply it with the weight vector, you add a bias to it because there may be some bias that you detect in the trainings, and you compute an output. If the output is greater than 0, you basically say this is a cat. If the output is less than not greater than 0, you basically say it's a dog. So one of my examples over here is detection of a language, classifier of a language. For example, you want to guess whether a language, the words thrown at you are German or not German, let's say. So you train this linear function with words that are German and not German. And basically, this perceptron associates how each element, each word is correlated with being German or not German. And then you throw a sentence to a vector, let's say, a vector including a number of words to this perceptron. And basically, based on that vector and based on the weights that are learned, the perceptron does this multiplication and adds a bias. And basically, if let's say most of the words are correlated with German, then its output says, oh, I'm hearing German, or I'm seeing German over here. Otherwise, it says it's not German. It's a binary classifier, basically, as you can see. Modern neural networks are multi-layer. I don't want to call them necessarily perceptrons, but multi-layer perceptron-like things. Essentially, you don't have a single layer, but you have multiple layers like this. So you have multiple internal weight vectors, as you can see. It becomes more like a matrix at some point. Okay, so basically, you can make decisions that are not just binary classification. Perceptron is binary classification, which works nicely for whether a branch is predicted taken or not taken. But binary classification is not always what you want. You don't necessarily want German or not German, right? You want perhaps what I'm hearing is German. Is it German or is it English? Is it Spanish? Is it Swahili? Is it Japanese? Basically, you want to have those n-ary classifications. So modern neural networks are n-ary classifiers where you have n different outputs as opposed to binary. Of course, they can do binary as well, clearly. But in the branch prediction context, so let's go back to branch prediction. Vector X is the branch history register bits. Different bits in the branch history register. It could be 16 bits. It could be 256 bits, whatever. Output is the prediction for the current branch. And the weights are the training that you have done to identify the correlation of each bit with the current branch, basically. What is the correlation of this particular bit in the branch history register? What's the effect of that on the potential outcome of the current branch? And we will see this in a little bit. So basically, it's relatively simple once you understand. So, and this is the example of a perceptron. Basically, you can see that we have the X vector over here. Weights are the ones that are trained based on inputs, and Y is our output, basically. So basically, whenever you see the bits in the history register, you multiply it with the weights, and then you compare the results to a 0 or essentially 0. If it's greater than 0, you predict it as taken. If it's less than 0, you predict it as not taken, basically. And that's the idea, basically. The high-level idea is to use a perceptron to learn the correlations between branch history register bits and branch outcome. And as I said, a perceptron learns a target Boolean function of n inputs. These are n inputs over here, you can see, and then there's a bias. And each input is a bit in the branch history register. Okay, so let's take a look at this, basically. Each branch is associated with a perceptron when you implement it. And this is the paper that introduced the idea dynamic branch prediction with perceptrons. It's a seminal paper also. A perceptron contains a set of weights, Wi. Each weight corresponds to a bit in the Gshare, global history register, basically. And this is trained. It represents, after training, each weight represents how much the bit is correlated with the direction of the branch. If you have a large positive weight, then you have a positive correlation between the bit in the history register and between the outcome of the branch, meaning they go in the same way, let's say. If you have a large negative weight, that means that this bit in the branch history register has a large correlation, meaning if the branch history register says taken, perhaps the outcome should be not taken. And depending on the strength of the weight or value of the weight, the correlation is that much higher or lower. Okay, so hopefully this is clear. And the prediction is basically we express global history register bits as 1 and -1 in this particular case, taken and not taken. And we take the dot product of the global history register and the weights. This is a vector product, basically, right? You have a vector of weights and you have a vector of inputs. Inputs is Gshare and the weights is weights, essentially. And you take the dot product of it. Dot product gives us a single value, dot product of two vectors. If the output is greater than 0, then you predict the branch that you're predicting as taken. So I think it's beautiful. And you can see that it's a single layer network. Why is it single layer? Because you have a single layer over here, a single layer of weights. You don't do any other processing after this. There's not another layer. In existing neural networks, you have inputs, and then you have another layer of basically you don't have just Y, but you may actually expand this to another vector. And then that vector gets operated on with another set of weights, and then you have another layer. And there could be other layers that do other types of computations as well, which I'm not going to go into. But tomorrow we will cover systolic arrays, where we will talk about neural network execution a little bit more. But this is a single layer network. Okay, so basically this is what it looks like in the system. You have the branch address. You select a single perceptron. Selected perceptron, whenever you're fetching from that address, selected perceptron is essentially your weight vector, and you compute Y. You basically multiply that weight vector with the history register, and that gives you the prediction. And the prediction you later, basically based on the prediction you did, you do some training as well. Basically, when you actually execute the branch outcome, you update the selected perceptron that is associated with the branch. And this is a training function. Basically, a training function gets updated, and it basically ensures that each bit's weight is updated so that it captures the correlation. Basically, whether the bit was taken, whether the branch in the global history register was taken, and whether the existing branch that you're predicting was taken or not taken. Depending on that correlation, you update the weights. And there's a weight update function that's proposed by this earlier paper that I mentioned. So that's the training, basically. Prediction is also simple, but it's not as simple as what we have seen so far. You need to do a vector multiplication, as you can see over here. So there's a bias weight. This is the bias of the branch independent of the history. And there's a dot product of global history register and the perceptron weights, as you can see over here. And then the output is compared to 0. This is called an activation function. What do you do with the output, right? What do you compare it to? It's called an activation function in neuron terminology, let's say. In this particular case, we compare it to 0, but it could be something else as well. So it's a beautiful idea. This is actually the first successful application of machine learning into real hardware that has impacted real processors like the Samsung Exynos CPU and AMD, as then we will see. The advantage is more sophisticated learning mechanism. You get better accuracy, and it enables long branch history length, actually. This way, you can actually do a multiplication, and the length of the branch history is now limited by how much multiplication you can do. You get better accuracy because of this long branch history length. In fact, when I was doing my PhD, I implemented this predictor because the ideas that I were working on required a good predictor. And immediately compared to a hybrid predictor, I myself personally observed that you get 20% reduction in misprediction rate. And that's quite significant at similar hardware cost or even less hardware compared to a hybrid predictor. So this is empirically proven. That's why people are implementing it. The downside is, of course, there's complexity now, right? How do you actually do this vector multiplication? It's actually an adder tree to compute the perceptron output. The latency may increase because of that also. So complexity in terms of hardware cost and latency is relatively high. But people are implementing it by using pipelining, etc., which we're not going to get into. The other disadvantage is because it's a single layer network, it can learn only linearly separable functions, basically. It cannot learn non-linearly separable functions. For example, it cannot learn XOR type correlation between two history bits and the branch outcome. If you don't quite understand what this means, don't worry about it or read more about perceptrons. But basically, learning is limited in this particular case. You cannot learn every possible correlation. That's the idea. But regardless, it's a successful example of use of machine learning in processor design. And if you're interested, I would recommend taking a look at this innovative architecture that includes perceptron predictor, that also includes some other predictors, including one predictor that we proposed for indirect branch prediction in 2007, for example. It's a nice paper that talks about a lot of ideas in branch prediction. And more recently, the Zen 2 and early on pile driver processors actually employed a perceptron branch predictor. As you can see over here, it has the first level predictor is a hashed perceptron. Hashed means you basically don't just use a program counter, but you hash information to get a weight vector, meaning a perceptron. And this is a nice picture from Wikichip that actually talks about how this operates, but it's essentially the same as what I just described, but you can also refer to other resources. Let me give you another idea. This is the idea of Tage. And the idea I already given you actually, basically predict using multiple history lengths. So observation is that single history length is not good for every branch. Different branches require different history lengths for better prediction accuracy. So why not have multiple pattern history tables indexed with different global history registers with different history lengths and intelligently allocate pattern history and table entries to different branches. If a branch likes a smaller history length, predict it using that history length. If a branch likes a large history length, like 500 prior branches, then use a bigger table for that. And this is what it looks like. I'm not going to go into the details of it. For example, there's a base predictor, which is indexed using PC, another predictor that's using small history lengths, another predictor using large history lengths. In this particular case, they propose a geometric history length, where the history length follows a geometric series. So you can easily get to 1,000 history lengths, for example. And these tables actually can be small because they're not true to the history length entries, because they're tagged in this particular case. And then the prediction is based on the confidence that you have. If a larger history length predictor actually provides a prediction, then you choose that one because it's assumed to be more accurate. Why? Because in the training phase and the updating phase of the predictors, you ensure that you don't allocate entries from the larger predictor for branches that can be predicted with smaller history lengths. That's the idea, basically. You need to be basically very careful. And this was proposed by this paper by André Seznek and Pierre Michaud in 2006, as you can see. And this is also a nice picture from Wikichip that shows that some branches require smaller histories, some branches require larger histories, because they may be correlated with more branches or branches that are farther away from themselves, right? That's the idea. Okay, so as with any idea, this has advantages and disadvantages. Here, we're exploiting the heterogeneity in the history length predictability of each branch. So we choose the best history length to predict each branch. You get better accuracy. That's great. It also enables long branch history lengths, which is good, better accuracy. So here, Tage and Perceptron have something common. They both enable long branch history lengths. The disadvantage of Tage is, again, hardware design complexity is not low. There are it's different kind of complexities in Perceptron and Tage, but they both are complex, I would say. But Tage can be implemented perhaps more easily because it doesn't require multiplications, let's say. And you need to choose good hash functions and table sizes to maximize accuracy and minimize latency. But this is also another successful recent idea that's used in many modern processor designs. And actually, AMD Zen 2 has both Perceptron and Tage. You can read over here, and you can also look at AMD documents, but you can see over here is that it's a two-level, multi-level branch predictor. Perceptron makes the fast prediction, let's say. Tage makes the correcting prediction. So if Tage basically provides a different prediction than the Perceptron, they don't explain it clearly, but this is one way it could be implemented potentially. They could overturn the prediction of the perceptron and have a mini small pipeline flush. So this is a multi-level predictor, as you can see over here. And this is another picture that shows the geometric series if you're interested. Always the question becomes, can we do better? I will quickly mention another work that basically uses similar ideas. You have the Tage predictor, PC global history. It provides you a prediction and confidence. And then basically you do some statistical analyses on the data. And based on that statistical analysis, some of them can be actually based on perceptron prediction. You basically either use the prediction that's provided over here or use the prediction that's you overturn the prediction. And loop predictors and other predictors can be predicted differently. And this is really the state of the art in branch prediction. So I mentioned confidence. So let me talk about confidence and then we're going to be done. But basically confidence is interesting because the idea here is to estimate if the prediction is likely to be correct. I mentioned this earlier, but you can estimate how confident you are in the prediction by looking at essentially some other information. Why? Because this could be very useful in deciding how to speculate, which predictor to use, which table to use, whether you would like to keep fetching, whether you should switch to some other way of handling the branch, or whether you should switch to some other thread, for example. And this is a very powerful idea because it enables a lot of other ideas, let's say. And it was introduced in this paper. So there are many different example estimators that are proposed, but you can keep a record of the correct, incorrect outcomes of the fast n instance of the branch. And based on that, those correct, incorrect patterns, you can guess if the current prediction is likely to be correct or incorrect. So this is not the prediction for the branch. This is the confidence in the prediction you're making for the branch. There's a difference. And one way you could use this is, for example, you fetched 5 branches into the machine and you're not confident in the predictions that you made, meaning it's likely that you're on the wrong path. And the decision-making logic in the pipeline can say, oh, I'm going to stop fetching because I'm likely on the wrong path because I fetched 5 or 10, some number of branches that I'm not confident of. It's likely that I'm on the wrong path and maybe I should not waste energy. So you can make this sort of decisions if you actually have some kind of introspection into the decisions, into the predictions that you have made. And this is called pipeline gating. Again, it's a very powerful and good idea that was published in 1990s. Okay, I think that brings me to the end. I don't hear anything over there, but I assume that the bell has rung at this point. I'm not going to talk about other ways of handling branches. I will basically refer you to some other lectures, and you can find those in the slides over here in the backup slides. So I think we're done. If there are any burning questions, I'm happy to take them. Otherwise, I will see you tomorrow. Okay, I think.
Hi, Onur. I don't think there are any questions.
Okay.
Yeah, maybe we can end.
Okay, sounds good. Then,
okay.
Then we're done. And feel free to ask questions over Moodle or anywhere, basically. Thanks.
Oh, I see. Okay.
Okay.